Hello everyone, this is Mr. Combs, and I want to talk to you in this video, and it actually may be a couple videos depending on how long it takes us to get through this material. But I want to talk to you in this video, or these videos, about real numbers and divisibility. Now, these are the first topics from Unit 1, the real number system and number theory. And I wanted to actually talk about these two concepts in class, but we had some technology issues. So I'm going to make a video, or I'm making a video. This video should help you with homework 1 and with part of homework B. There's also another video that I had planned to have you watch that will also help you with homework B. But after this video, which I'm going to call video 0, because I already have a video 1, so after this video you should be able to do homework A, and then after comparing, or after watching this video and video 1, you should be able to do homework B. Alright, so let's talk about the real number system. So a set is a collection of objects called elements. And we usually have sets of numbers, but a set can be anything. So for example, I could have the set A, and we usually let a capital letter represent a set. So I could have the set A be, I don't know, this star, this circle, well, sort of a circle, this square, and this triangle. So this is a set. And when you put a set in between curly braces, that's what these little symbols are called, you are representing the set using the roster method. And I'm not sure if I talked to you about that anywhere in this video, so I'll just write it here. So this is the roster method, R-O-S-T-E-R. And I'm writing with my mouse, so I'm not going to be writing as clear as I could if I had a pen. And basically the roster method is just where you list the elements of a set in between curly braces. Okay, so this would be the set A. The elements are star, circle, square, triangle. Alright? So we're going to primarily talk about sets of numbers in the real number system. So to make the study of numbers more efficient, we divide numbers with similar properties into the same set. So the first set of numbers we will work with is probably the first group you encountered as a student and as a human living in the world. And these are the natural numbers. Now we let sets of numbers be represented by a capital letter. So the natural numbers, the symbol for the natural numbers is N. And the natural numbers are basically those numbers that you would think of as numbers. They're naturally what you think about when you think about numbers. Sometimes they're called the counting numbers because they're the numbers we use to count. So the natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and so on. If you notice, the smallest natural number is 1, but the list of natural numbers continues on forever. So for every natural number you can think of, you can always think of the next number higher. You can always add one more to that number. So there is no largest natural number. The set of natural numbers is very simple. They're very simple numbers. However, it has also been described as elegant by mathematicians. In fact, an entire branch of mathematics has developed to study the natural numbers and their properties, and that's number theory. And that's what we're going to focus on in this unit. Alright, you'll notice that there's one very common number that's missing from the list. That's 0. 0 is not a natural number. Zero as a fully developed concept really is a relative newcomer on the number scene. Many ancient civilizations had numeration systems that didn't even have a clear concept or symbol for zero. Today, zero is an important number used to represent nothing. So it's, if I say I have 0 cupcakes, then I don't have any cupcakes. But it's also used as a placeholder. So, for example, we couldn't tell the difference in our number system between 44 and 404 if we didn't have 0. So when we add 0 to the natural numbers, we get the whole numbers. And the whole numbers are basically defined as the natural numbers and 0. So notice that every single whole number is also a natural number, right? So in this case, 0 is the new addition, but all of these numbers are also natural numbers, okay? So if I were going to draw sort of a diagram of this, I might say I have the natural numbers. They're in their own little circle. But then I also have the whole numbers, and the whole numbers include all the natural numbers, and they also include 0. Okay? So the whole numbers are 0 and the natural numbers. So 7, for example, is both a natural number and a whole number. 0 is just a whole number, right? For right now. 0 also falls into other categories, but for right now, it's the new addition. 9, for example, again, is both a natural number and a whole number. So notice that 0 is the smallest whole number, but like the natural numbers, there is no largest whole number. Also notice, and we said this before, that every natural number is also a whole number. So what's missing from the whole numbers is the negative parts, right? So negative numbers are important for us to represent quantities when we're in the hole, or quantities where we owe something. If you have a negative balance at the bank, then you owe the bank, right? So the integers are represented by a z, and I'll tell you why that is in just a minute. But the integers are usually defined as the positive and negative whole numbers and 0. So remember, 0 is neither positive nor negative. Sometimes the integers are referred to as the whole numbers and their opposites. Recall that two numbers are opposites if they have the same absolute value, or if their sum is 0. So if I take a number and add it to its opposite, I will get 0. So 4, for example, and negative 4 are opposites, since they both have the same absolute value. And if I add 4 and negative 4 together, I get 0. So you'll notice that the integers, they are represented in the roster method. So I have ... negative 5. So they actually go on to infinity in the negative direction. So negative 6, negative 7, negative 8, negative 9, and so on are integers. And then 5, 6, 7, 8, 9, 10, and so on are integers. So you'll notice that every single whole number is also an integer, which means every single natural number is also an integer. So if I were adding on to my diagram here, I would say that the integers are another set that involve all of the whole numbers, all of the natural numbers, and then for the integers, though, I also have the negative numbers. So, I have negative 5, negative 4, negative 3, and so on. ... and I'll say ... here, okay? So, like I just said, notice that the integers extend indefinitely in both directions. Also, there is no largest integer, but there's no smallest integer either. And also notice that every whole number, and thus every natural number, is also an integer. And the reason why we let a z be used to represent the integers is to honor the contributions of German mathematicians in the fields of algebra and number theory. And the German word for number, which is Zahl, begins with z. So we can count things using the numbers we have so far. We can represent nothing, and we can even represent values that are less than nothing with negative numbers. However, here we're still dealing with whole numbers. We have no way to represent parts of numbers. For example, with the numbers that we've talked about so far, we could not represent the measurement of a board that is 3 3/4 feet long. We have no way to represent 3/4. So we need to introduce a new set of numbers, and those are the rational numbers. So the rational numbers are those numbers that can be written as the ratio of two integers, and they help us to represent parts of numbers. Unlike previously mentioned number sets, the elements of the rational numbers cannot be listed nicely in order. So we can't really list the rational numbers in the roster method because they don't fall in a nice order. So, I have 1, 2, 3, 4. That's a nice order of numbers for the natural numbers. But I can't simply say like 1/2, 1/3, because in between 1/2 and 1/3, in fact, I would probably say 1/3, 1/2, because 1/3 is a little smaller than 1/2. Because in between 1/3 and 1/2, there are a whole bunch more rational numbers. There are, infinitely many more rational numbers. So I can't really use the roster method to represent the rational numbers, so I have to use another method. And the method that I have here displayed is called set builder notation. So this is the set builder notation. And set builder notation is named because we can use it to build our set. So if I had a pile of numbers sitting there, I could pick up a number, I could test it against this rule. If it fits this rule, I put it in the set. If it doesn't fit the rule, I throw it out. So the set of rational numbers is defined as any number that is a ratio of two integers. So anytime I have one integer on top of the other, and the bottom integer is not 0 because I can't have 0 in the denominator of any fraction, I have a rational number. So rational numbers are basically any number that can be written as a fraction. So here I have that listed here or written out. Basically, a rational number is any number that can be written as a fraction. And this is why Q is appropriate as a symbol for the rational numbers. The fraction bar represents division, so fractions, and thus rational numbers, are basically just quotients, right? So let's talk about what a rational number looks like. What numbers can be represented as fractions? Well, obviously, fractions can be written as fractions. So all fractions are rational numbers, whether they're negative or positive. So 1/2, 29/25, negative 9/17, all of those are rational numbers. Likewise, mixed numbers can be written as fractions. So all mixed numbers are rational numbers. And one of the types of problems you'll have in your homework are problems asking you to represent a mixed number as a fraction. So let's take a look at 4 3/5, and let's talk about how we represent that as a fraction. If you want to represent 4 3/5 as an improper fraction where the numerator is going to be bigger than the denominator, because this is going to be a value that's bigger than 1, a proper fraction is always a value less than 1. What you're going to do first is you're going to multiply the denominator by the whole number part, and then you're going to add the numerator. So the first thing I'm going to do is say 4 times 5, that's 20, and then I'm going to add the numerator, that's 3, so I'm going to end up with 23, and then you're going to write 23. Step 2 says to write this sum over the original denominator. So 23 over 5, or 23/5, is the fraction that is equal to 4 3/5. Alright, I'm going to end this video and check out the next video in order to see a continuation of this topic.